This is the last chapter in Chem 102, Electrochemistry, chapter 18 in your textbook. So, we've got in fact, this is not the same. All right, that'll work. That'll work. First of all, the definition, electrochemistry. That's the study of the interchange of electrical energy and chemical energy. And how we can transform one into the other, even make use of the electrical energy that can be obtained from a chemical process. And in order to do that, of course, we need to define some terms. Rather than just jump into this one, let's look at the difference between oxidation and reduction. Oxidation, in chemical terms, refers to any process in which electrons are lost from a species, an atom, or a group of atoms. And then reduction is the flip side of that coin. Any process that causes the gain of electrons is called reduction. That always occur together. You can't have one without the other in a chemical process. Because in chemistry, we don't build up static charges. If electrons move, they have to go somewhere, and they have to be neutral in the process. So the best way to remember that is this little mnemonic, oil rig. Oxidation is loss, and reduction is gain. The interesting thing about that is in terms of, let's use a generic equation at first. Let's say A and B yield C and D. And in the process, A loses electrons. So this one is oxidized. And this one must be reduced. So electrons have to be transferred from A to B. When that process occurs, we refer to the chemical that is oxidized as the reducing agent. Because it was the agent for, where it caused the reduction of B. And vice versa. This one, B, becomes the oxidizing agent. Okay, so if this happens, now A has lost at least one electron, maybe more, and it has become deficient in electrons. And B has acquired an excess of electrons. This doesn't always result in a charge, though. Now, if we have a metal and a nonmetal, like that, so this is a solid, this is a gas. We react those together, and we do get a complete transfer of charge. Right? We need two of these and two of these, and this is also a solid. Okay, so in that case, you do get a transfer of electrons to form ions. But characteristic of oxidation and reduction reactions, and that's what we call these, redox for short, oxidation and reduction reaction, while we may transfer electrons, we don't always form a charge as a consequence. And I'm going to show you a way to track how these electrons move in a reaction in just a second. Okay, let's look at it in terms of this real example. The way we make sense of a redox reaction is to divide the reaction into halves, half reactions. One half represents the oxidation step, and the other half represents the reduction step. Now, both of these half reactions occur simultaneously in the reaction mixture, but we pull them apart so that we can track the movement of electrons and make sense of it. Like I've always said, nature just does what it does. And this is one of the ways we use to make sense of what nature is doing. So if we have a balanced equation, here, this example, and one thing I notice immediately here is the charges, right? You got 8 pluses and 10 pluses, so that's 18 pluses. Do you have 18 pluses on this side? Well, let's see, 5 times 3. 3 times 5 is 15, and 2 is 17. Oh, but we got the 1 minus. So you have the charges balanced. Okay, but there may be some missing spectator components to this reaction that aren't necessary to understand the reaction. In which case, we might use potassium manganate as our source here. We might use iron 2 nitrate as our source here. The nitrate and the potassium are spectators, so we don't include them in the reaction, just to simplify things. Okay, so if we know this is the balanced equation, then how do we identify which one is the reduction and which one is the oxidation? Well, the simplest way is to look at the charges, if they're available. This iron is a 2+ ion here and a 3+ ion there. So how did it get there? It had to lose an electron. Remember, we don't gain or lose positive subatomic particles. Otherwise, if we do, the only option we have is protons. And if you add or subtract protons, you have different elements. So we can't mess with those. Electrons are the only things that can move and change the charge. So here we would have to lose an electron from iron. Where did it go? Well, it had to go here to manganese. Because here, manganese is a given charge, and there it's a 2+. Now I'm going to show you how to track those charges. It's called oxidation state. And let's see. You know what? I don't see oxidation state in here anywhere. I wonder if it got left out. Bear with me a moment. Unless we covered oxidation state in Chem 101, that's possible. What I'll do now is review, just to be sure. Yeah, we better do that. Okay, so for any ionic compound, ions, covalently bound compounds, it doesn't matter. Determining oxidation state is simply a method of tracking electrons. It's a bookkeeping scheme. It's one of 2 or more possible bookkeeping schemes. In this case, we use it for inorganic chemistry. Okay, so what's the first rule? Rule number one. Elements in their most stable form at 1 atmosphere pressure and room temperature, 25 degrees C. Elements have an oxidation state. Let's do it this way. Let's put 1 down here. They're always oxidation state 0. 2, ions. Ions of elements. Their oxidation state is always the charge. So our example was sodium, Na+. The oxidation state of that ion is +1. I'll put an example. That implies +1 oxidation state. Then we have to look at other elements in the periodic table, and we have to fix their oxidation states. If we don't do that, then when they combine with other elements in the periodic table, we're stuck. We don't know which one belongs to which. So for some of the elements, we fix their charge. For fluorine, in any compound, fluorine has an oxidation state of -1. Oxygen has an oxidation state of -2, except for peroxides. Right? If you have a compound where you have 2 oxygens bound together in that molecule, each one of those oxygens is a -1. Both of them together is -2. Okay? Let's see, fluorine, oxygen, alkaline metals, always +1. Alkaline earths, +2. Okay. Now, what do we do about combinations of atoms? 7. For neutral compounds, sum equals 0. All the oxidation states together for a neutral compound must be equal to 0. How about polyatomic ions? Sum equals the charge. So the charge on the polyatomic ion is your target when you're adding all the oxidation states together within the polyatomic. Okay, I think that covers everything. So with those rules, we should be able to calculate the oxidation states for any of the other elements in the table, with a couple of exceptions, and we'll encounter those as we go. And in those cases, we're forced to make a choice and just assign a value. Okay, so I'll give you examples of that. For instance, I'll just give you one right now. How about this one? PCl5, right? Neither one of those are in our assigned values. Chlorine is a halogen, which typically is -1 charge. So rather than assign something to phosphorus, which could be variable, we prefer to assign a charge to the more electronegative. So we're going to say -1 for chlorine. That means -5 total, 5 times -1. That means phosphorus has to be +5. That's the way we bookkeep. Okay. So now that we have those rules, I may have given you those rules in Chem 101, but it never hurts to review. I just need a marker that works. Okay, so how do we use that information to balance an equation where we know electrons are being transferred? Well, first of all, you have to find out, are electrons being transferred? If they're not, then you don't need to use this method. Okay? So if you know that electrons are being transferred, and how do you know that? Let's go back just for a second. I mentioned this one, right? That's 2+, oxidation state. How about this one? MnO4-. What's the oxidation state on manganese? Well, oxygen we've taken is -2, times 4 is -8. But the total has to be a -1. So we need to hold one of these minuses out for that charge. That means we only need to balance a -7. And that leaves an extra minus for the charge on the ion. So that means that manganese is +7. So what's happened is the manganese has gained 5 electrons for each manganese atom to go from +7 to 2+. Okay? That's how we know to put the manganese here in this reduction and the iron here in this oxidation. Now, how do we know where the oxygens and hydrogens go? Well, you see that oxygen there. We have to account for that oxygen somehow. And I'm going to show you in just a minute. We account for it as water. But if we do that, we add hydrogens. So now we have to account for the hydrogens over here. So I'm going to give you the rules in just a second. Iron changes from 2+ to 3+. So all we need to account there is electrons. So when we reduce, electrons are reactants. In other words, these electrons are being added to that manganese. And now they're embedded in the Mn2+. Over here, oxidation is loss. So the electrons are part of the products. This iron lost electrons, now they're free, so to speak. Okay. The other thing I will point out is that the number of electrons, if we add these equations back together to get that target, the number of electrons gained has to be equal to the number of electrons lost. Otherwise, you can't add those equations back together. Okay, now for the rules. How do we balance an equation? Well, you take the equations given to you and you decide, is it an oxidation reduction reaction first? Okay, if it is, then you say which species are being oxidized, which are being reduced. Then you separate the equation into 2 half reactions, one for the reduction, one for the oxidation. Then when you balance them, you balance all the elements first, except hydrogen and oxygen. If there are no hydrogens and oxygens in the reaction, in the half reaction, then you go ahead and balance the elements and you're done with that part. But if there are, balance all the elements except hydrogen and oxygen. Then you balance oxygen using water. So if you have oxygen on one side of the equation, you put water on the other side to balance the number of oxygens. And then since you added hydrogens, now on one side of the equation, you got to go back to the opposite side and add those same number of hydrogens back over here. And you balance them as protons, H pluses. Then you balance the electrons. All right. Now, before you can put these equations back together and make a complete balanced equation, you may have to multiply the entire equation through by some constant. It could be a whole number, could be a fraction, whatever it takes, in order to equalize the number of electrons in each one. Okay, we're going to do some examples. Then when you add them back together, you look for any species that can be canceled or reduced in some form. You have waters on both sides. Then you say, all right, which one has more? Use up all the ones on this side and subtract them from the ones on the other side. And then you check to be sure that you brought everything together properly so that the equation is balanced. Check your work. All right, here it is in flowchart form if you're interested in that. Okay, here's an example. First step, separate them into half reactions. All right, how do we know half reactions? Well, we have to do oxidation states first. All right, so let's put our equation up here. This is what's given to us. All right, this is the dichromate ion. This is the sulfite ion. Chromium 3+. Everything is occurring in solution. And this is the sulfate ion. Okay. Now, let's do oxidation states. Ions are easy. Simple ions like this, that's 3+. How about the chromium over here? Well, 7 times -2 is -14, but we need to hold 2 minuses out for that charge. So we really only have to balance a -12 with the chromium. So the chromium has to be +12. That means with 2 chromiums, each one is +6. Okay. So that says that chromium is going from +6 to +3. How does it do that? It gains 3 electrons for each chromium. So reduction is gained. This is our reduction half reaction. We're going from dichromate ion with a +6 here, and we're going to chromium 3+ here. I'm going to leave out the aqueous part because it takes up too much room. Okay, that's our reduction. That means the oxidation has to be the sulfur-containing polyatomic ions. So oxidation is going to be sulfite yields sulfate. Right? We need to know what the oxidation states are. So let's go ahead and do those. -2 times 3 is -6, but we have to hold out 2 minuses for the charge. So we only balance -4. That means +4 for that sulfur. How about this one? -2 times 8 times 4 is -8. Hold out 2, -6. So this one is +6. All right. So now we know our oxidation states. All right. So first things first, balance the elements that are not oxygen and not hydrogen. Now, all of these steps are in subsequent slides. I'm doing it on the board here in logical sequence. And then if you need the slideshow to support it, then we'll go through those rather quickly. Okay, if we're going to go 2 chromiums here, we need 2 chromiums here. Okay, that's it. We don't balance the oxygen yet. 1 sulfur here, 1 sulfur here. We're done. Okay, now balance the oxygens. 7 oxygens. Okay. So we have 7 waters. Right? 7 oxygens, 7 waters. 14 hydrogens were added on that side. So this side has 14 hydrogens. Okay, now let's go to this one. What's the difference here? We had 3 oxygens here and 4 there. So we actually had a water on this side. 1 oxygen, 4 oxygens. Okay? So now we added 2 hydrogens. So we added 2 hydrogens there. Okay? Now we do electrons. Okay. How many electrons were added to this one? Well, we went from +6 to +3, which is 3 electrons for each chromium, but there are 2 chromiums. So 2 times 3 is 6. 6 electrons had to be added to these 2 chromiums to make those 2 chromiums 3+. How many were lost on this side? Well, we only lost 2 electrons for each sulfur. Okay? All right. Now, before we can bring them back together, we have to balance the electrons. Here we have 2 electrons lost versus 6 electrons gained. So how do we balance those out? We need to multiply this entire equation by 3. 3 times 2 is 6. Okay? So if we do that, what does that do for the coefficients? Now we have a 3 here. We have a 3 here. We have a 6 here. We have a 6 there. Okay? 6 electrons gained, 6 electrons lost. Now we can add the equations together. All right, let's put them in this same order here. So we have dichromate. Plus 3 sulfites. Okay. Plus a water. Plus 14 hydrogens. And the electrons cancel. Right? Same number of electrons on both sides, they cancel. We don't have to bring them down. Now on this side, let's see, 1, 2, 3, 4. 1, 2, 3, 4. This side we have 2, 3 plus chromiums. We have 3 sulfates. We have 7 water. And we have 6 hydrogens. Okay? Let's see. 1, 2, 3, 4. 1, 2, 4. Now let's see if we can reduce this equation any further. Cancel objects. We can't do anything with that one or that one, this one or this one. That water. 7 waters, 1 over here. This one goes away. This one now is 6. 14 hydrogens and 6 hydrogens. Those 6 go away, and we're left with 8. Okay, so our balanced equation is 1 dichromate, 3 sulfites, plus 8 hydrogen ions yields 2 chromium 3+ ions, plus 3 sulfate ions, plus 6 waters. All right. So here we have the first step where we separate the into half reactions. Then we balance. Let's see, this one is actually this one's getting the electrons first. It'll still work. I just like to do the electrons last. Now notice one thing. If we have hydrogen ions here, remember all of this is in aqueous solution. It's all together. We're describing it as reactants to products, but everything's together. So if we have these hydrogen ions, what are we doing? We're conducting this reaction in an acidic environment. Excess hydrogen ions, protons. Okay? And let's see. It does not agree with me over here. 4 waters. Okay. Oh, I did make a mistake. There should be a 3 here, which makes a 3 here, which makes a 4 here. Attention to detail. All right, so that's our balanced equation by the half reaction method. Some of these reactions, now you can't balance the original equation and end up with this one by any other method. This is the only way to do it. If you're given every species that is known to be there without the coefficients, then possibly you could balance it by our standard budget method. But anytime electrons are transferred, this method works better. Even if you use the account for transferred electrons first and then follow it with budget method. That's sort of a hybrid procedure. And I'll let you know if we run across one of those. And we may not see one until we get into a review problem next week. Okay. So you may be wondering, if this occurs in acidic solution, could we balance the equation for a basic solution? Yeah, as a matter of fact, we can. In fact, the method for balancing in basic solution is what I call the fake acidic. You do the acidic first, and then you convert it to basic. So let's do, since we've got this one on the board, let's go ahead and do this one. All right. Let's see, these 3 waters are gone. Now we have 8 hydrogens here. All right. I'm just cleaning it up. So this one's now 4. And those hydrogens are gone. Okay. Now, once you balance in an equation acidic, you can convert it to basic simply by neutralizing all of these hydrogen ions with hydroxyls. So if we add hydroxyls here to neutralize those, then we have to add hydroxyls over here. Okay? Now, what does this give you? Remember, any acid-base reaction produces water as a product. So you have 8 waters. And over here, you have 4 waters. So now this becomes 4, and these waters go away. So now we have the equation written for basic solution. Water's on this side now, and hydroxyls on that side. But like I said before, those hydroxyls are in solution with everybody else. This just means that the solution is basic. Now, I don't know if this equation can be conducted in basic solution. Maybe it won't go. It's not spontaneous in basic solution. But technically, this is correct. The conversion we made is the way you balance an equation for basic solution. If you're given a problem, then it will say, balance this equation by the redox method, the half reaction method for basic solution. And you would balance it for acidic solution first, then convert it to basic. Now, I'm sure there's a way to do it straight to basic solution right off the bat, but I think it's simpler to do it this way, and the chances of mistake are much less. Okay, how about this one? Oh, they're expecting me to do this one on the board. We already did one on the board, so I'm not going to do this one. What you have here is acidic solution. There's your hydrogen ion. And here the fake acid method, I call it, are the steps for balancing for basic. First, you balance it for acidic, and then you neutralize the protons with hydroxyls. Okay, and this is the flow chart with the added steps down here for basic solution. All right, so I think we're done with that one. Okay. Oh, I see. What if we tried to balance it with hydroxyls instead of hydrogen ions? If you added these instead, what could be the potential problems? Well, you have to add water to the other side to compensate for the oxygen addition in OH minuses. Then you've got to, what are you going to do with the hydrogens that you put on the other side? Say you have hydroxyls added on this side, like that. Everything else over here. And you add water over here to balance those, right? Well, what have you done? You've added extra hydrogen. So now what are you going to do? Well, you have to put hydrogens over here, I guess, and neutralize that hydroxyl. That's the way I would do it. So if we added 2 of these over here, then I'd add 2 of those, and that would neutralize one of these, leave one of those, and make a water. So it can be done. I just think it adds extra work, and the chances of making a mistake are much greater. Okay. So if we balance this one in basic solution, let's see, is it going to give us steps? No. Okay. Rather than take time to do this one in basic solution, just use the same method as before. Find out what your half reactions are, balance them according to the acidic procedures, and then convert it to basic. And you should end up with this equation. And there's your basic proof right there. Okay, now that we know how to balance redox equations, we're going to use that information to extract energy from the process, right? At this point, we haven't done anything with the electrons. I mean, they're lost. If you put all those things together in one solution, the electrons are transferred and energy may be absorbed or released in the process, but we don't have access to it, because those electrons are going, and we can't grab them. So the galvanic cell, also called a battery, allows us to access those electrons. So how does it do that? Well, this device takes a spontaneous reaction. Right? We wrote the equations as reactants yield products so that this will occur spontaneously from here to here. Okay? The reaction is driven from left to right. And the way to make a galvanic cell is to take those half reactions and actually physically separate them. Put one half reaction in one jar, the other half reaction in the other jar, and the only way that they have access to electrons to complete their reactions, their half reactions, is via an external wire. So we control the flow of electrons between the two. So the external wire goes from one to the other, right? If it goes through the wire, that means it had to be lost from this side, right? That's the oxidation side, and it goes to the reduction side. And the electrons are supplied over there so that they can be added to the reactants and make products on that side. That, in a nutshell, is a galvanic cell, where you separate the half reactions so that you can access the electrons. When electrons move, we can make them do work. Okay. Let's see. Here's an example. The one fly in the ointment is that you cannot get charges to move or current to flow in a wire unless it is a complete circuit. That's just a fact of electricity. So we can have this external wire to access the electrons, but the reactions are not going to proceed unless we can complete the circuit. So we do that either with what's called a salt bridge. We form a pathway for the movement of ions. And the movement of ions maintains the balance of charge and allows current to flow through the wire. The salt bridge will do it, or we can just put a porous disc between the two half reactions. It does not allow substantial mixing of the two half cells, but it does allow free movement of ions. Okay. So there we have a completed galvanic cell. So how does the salt bridge work? Well, if we are actually allowed to go into the lab and do the last lab exercise, we will construct a battery using a salt bridge. And the way we do it is we take a strong electrolyte, in our case, potassium chloride, dissolved in water, and we heat that up and we add agar to it. Agar is simply a colloid that allows us to turn a liquid into a solid, but it still allows free movement of ions. Now, sometimes the salt bridge is completely liquid, and they just put plugs in either end of the U-tube. But I like to use a complete agar salt bridge. It's easier to build, actually. All right, so porous disc is self-explanatory. Now, of course, we have more names to learn. When electrons are transferred through that wire, in this case, they're moving from left to right. And on this side, the electrons are provided as reactants into that half cell. And this side is where reduction occurs. Okay? Reduction then is given the name cathode. This is the cathode, that half cell. That's where reduction occurs, and that's always the case. no matter what else we do, cathodes always are the half cell where reduction takes place. Consequently, on this side, where electrons are removed, oxidation takes place. That's called the anode. Okay. So the anode is where oxidation occurs. The cathode is where reduction occurs. Now, sometimes this, what we call the electrode that's submerged in the solution participates in the reaction. That's possible. But we can have a half cell where all the, in this case, all the cathode reaction, half cell reaction takes place in solution and the electrode doesn't participate. So in that case, we just need some electron conductor that will not corrode easily. In the laboratory, many times we use platinum because it's a noble metal. But in a cheaper source would be a carbon rod. That's what's used in dry cell batteries. The carbon rod doesn't participate in the reactions in that battery. It just serves as a conductor. Okay. All right. So when two half cells are connected in a galvanic cell and electrons start to flow, there will be a certain amount of push from that chemical reaction to drive those electrons over from the anode to the cathode. And we can measure that push as a voltage, an electrical potential. We can calculate that voltage, what we would expect it to be. And it's given this fancy curly E for the cell. Okay. It's kind of hard to find that one. I'm not sure where I found that, but it's easier just to write a capital E. So when I write a capital E, that's electrical potential. And it has the value of volt. Okay. Sometimes it's referred to as electromotive force. Right? That's the idea of the push. The force that's pushing those electrons from one cell to the other. Okay, this unit of electrical potential, the volt, can be converted or can be represented by other units in the SI system. 1 joule of work per coulomb of charge is 1 volt. So 1 volt equals 1 joule of work for each coulomb of charge transferred. Now, coulomb is a unit of measure of charge. It could be a negative charge, it could be positive charge, doesn't matter. We'll give you the equivalent for that one in just a few minutes. But this is what it means. So, like any relationship, if we want to know how much work is being done, we just need to know what charge is transferred times what voltage is behind it. That times that will be the joules, or the amount of work that can be extracted from this process. Okay, we got a little video.
A useful galvanic cell can be constructed by using zinc and copper. The anode is a zinc bar placed into a zinc sulfate solution. And the cathode is a copper bar placed into a copper 2 sulfate solution. The two solutions are connected by a porous sodium chloride salt bridge that prevents the two solutions from mixing but allows ions to migrate. Attaching the cell shows that electrons flow from zinc to copper. Because zinc is a more active metal than copper, it is more likely to lose electrons. For this reason, the zinc bar is oxidized, producing a zinc ion and 2 electrons per zinc atom. The copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. Positive sodium ions migrate into the copper sulfate solution from the salt bridge, while negative chloride ions migrate from the salt bridge to the zinc solution and maintain neutrality of the solutions. The reaction stops when the zinc bar or copper ions are depleted. The overall cell reaction can be written like this.
The zinc was oxidized. And the copper, is that right? No, that's wrong. One more second. Well, I lost my place. That's right. That's right. Zinc was oxidized. Copper was reduced. Copper 1, copper 2, I think. There. Okay. So those are the 2 half reactions. Really simple. Let's see, now where was I going with this? This, since it's oxidized, represents the anode. And typically, when we draw the diagram of the galvanic cell, we put the anode on the left and let the electrons flow from left to right. So this is the cathode, which will be on the right. Okay, so how do we measure this stuff? There are a number of ways, instruments that will measure that push, the voltage, the electrochemical potential. One way is with a voltmeter. The voltmeter is very inexpensive to produce. So if you go to the store and buy what's normally referred to now as a multimeter, it will have a voltmeter built into it, and it uses this technology. It uses Ohm's law. So if you haven't had any physics, you won't understand. Let's see. E equals IR. It's the way I remember it. Ohm's law, where the voltage is proportional to current, and the resistance is the constant value. So if we have a known resistance and we draw a certain amount of current that's measured in the circuitry, then we can infer, actually we can calculate the voltage, and the instrument does that for you. a more accurate way. In fact, the problem with the voltmeter is that when electrons are moving, you induce other variables in the reaction that can adulterate your results. So this is not the most accurate way to measure voltage. A more accurate way is with a potentiometer based upon potential, measures the potential. What you have is a device that has a built-in voltage source that is very well calibrated. And what you do is the reaction is spontaneous in this direction, produces a voltage in this direction, right? Voltage to the right. The potentiometer supplies in line with your cells there's your meter. The potentiometer supplies a reverse voltage, and you adjust the voltage until the current stops. In other words, you're opposing this voltage. You supply an opposing voltage to the left that opposes the movement of those electrons. And your instrument is calibrated so that the voltage is very well known, sometimes to 3 or 4 decimal places. And once you stop those electrons moving, you see the current is no longer moving from one to the other. At that point, when it's 0, then the opposing voltage is equal to the cell voltage, only with opposite sign. So the advantage to this is now electrons are not moving and you're not introducing any of those other variables that I mentioned earlier. There are thermodynamic considerations to be considered when you move electrons like that. The reaction is not reversible in those situations. So the maximum voltage that can be obtained from the cell is actually not measured here. It's measured here. That's the maximum voltage when, thermodynamically speaking, when the reaction is reversible, when it's infinitesimally small movement, forward and backward. Now we actually measure the maximum voltage. That's important for calculating the maximum amount of work that can be done by that reaction. Okay. Okay, so we use a voltmeter because it's cheaper, right? These potentiometers are expensive, plus they have to be strictly maintained and calibrated periodically, right? Because you're measuring a reverse voltage in the process of tweaking the dials. And if it's not properly calibrated, then the potentiometer is worthless. You might as well use a voltmeter. Okay. So these reactions, these galvanic cells can be measured voltage, but we can also calculate the theoretical voltage that's available. But first of all, if you've got copper on one side and zinc on the other, you know, which one's your reference? Because otherwise, you have to construct galvanic cells for every possible combination of cathode and anode, and then list them in a volume that would be the size of this room. So there's a better way. a more efficient way to determine the potential of your cell, the electromotive force that's provided by that combination of anode and cathode. And that's called the standard reduction potential. And it's just what it says. It's the potential or the voltage that is obtained for that half cell in terms of reduction. In other words, it'll give you something here and then plus electrons and yield something here. It's always written that way. And there's a voltage associated with it. But that little zero means under standard conditions. Right, what are the standard conditions? All the solutions are 1 molar in concentration. All the gases are at 1 atmosphere. That's right, gases. You can form an electrode from a gas. It's not easy, but it can be done. Okay? And okay. So when we reference these half reactions, we put them in a table, and there's a table in your textbook with most of the common half reactions. But what's our reference, right? The first thing I said about these galvanic cells is that if you don't have a complete circuit, nothing's moving. You're not going to get a voltage. So the half cell has to be compared to something. So we pick a standard half cell, and all of them are compared to that half cell. That's where this value comes from. The standard half cell is the hydrogen electrode. And the hydrogen electrode is arbitrarily set at 0 volts. So its half cell potential is 0 volts. So whatever you have for the other half cells can be compared to one another. And I'll show you how to do that. Okay, so I left out temperature. Right? 25 degrees Celsius is standard temperature. 1 atmosphere pressure, 1 molar concentration. So the standard hydrogen electrode has to be a gas electrode, and the hydrogen has to be maintained at 1 atmosphere pressure. Okay, if for some reason, when we combine half reactions, right, which is what you have to do, combine half reactions, one of them is going to be maintained as reduction, and the other one was going to have to be flipped to be an oxidation. Okay? When you do that, you change the voltage sign. If the voltage is negative, it becomes positive. If it's positive, it becomes negative. Whenever you flip the equation, just change the sign of the potential assigned to that half reaction. Okay. We're going to prove this later, but for now, accept that when you combine 2 half cells, the spontaneous direction of electron movement between anode and cathode is the one that gives you a summation positive voltage. The voltage must be positive for the reaction as written to be spontaneous. Okay, we need some examples. All right, so let's take the one that was given in that video, the zinc and copper. Let's look down. Notice the way they're listed, right? They're all reductions. I know this is kind of small, but it's in your textbook also. They're all written as reductions. So here, the fluorine diatomic molecule plus 2 electrons yields 2 fluoride ions. And the half cell potential is 2.87 volts under standard conditions. Notice that we start from high positive and we go lesser and lesser and lesser, smaller, smaller positives until we get to the standard hydrogen electrode. And written as a reduction, the standard hydrogen electrode is 2 protons plus 2 electrons yields 1 hydrogen, 1 H2 atom. Okay. So once we get past the 0, everything starts getting negative. More and more and more and more negative. It's still decreasing, but now we're in the negatives. Okay. The next one shows you the rest of it. Let's see. Oh, wait a minute. No, I didn't. Hold on a second. Let's see. This one goes down to 1.23 and then 1.21 on down here, there. 0.52 and then 0.40. Now down to 0. Now we carry on with the negatives. Negative 0.44. Now we go to negative 0.5 on down to negative 3.05. Okay? Now, that video also mentioned a concept, the more active metal. What do we mean by that? Activity in a metal is the tendency for the metal to give up an electron. So the more active the metal is the one that's going to release its electron more easily. We can think of that in terms of electronegativity. Right? The smaller the electronegativity, the more metallic. That is, the less the attraction of the atom for its electrons. So cesium would be around 0.7 on the Pauling scale. And above that would be other metals that are less metallic, so to speak. And as you move from lower left to upper right, become less and less metallic. So related that to these values, the more positive, wherever you have a metal, the more negative the value here, the more metallic. So the more active metals are down and the more less active are up. Because we're written as reductions. And the negative means it's less likely to acquire an electron. It wants to give it up. Okay. So let's take our example. Our example had zinc and copper together. Okay. So zinc, let's see. Here's copper. That's not the right one because we want copper metal over here. So let's keep looking. Here we go. Copper 2 plus 2 copper, 2 plus 2 electrons yields copper metal. 0.34 plus 0.34 volts. Okay? How about zinc? Well, let's find zinc. Where's zinc? Zinc. I don't see zinc here. Let's go down. Oops. Zinc. No zinc there. Zinc. Where is zinc? Well, there it is, right there. So written as a reduction, zinc 2 plus 2 electrons yields zinc metal, and its voltage is minus 0.76, minus 0.76 volts. That's the way they're written as reductions. But we know, based upon that video, that zinc should be flipped. It's actually not a reduction, but an oxidation that takes place with the zinc metal. So what we would do is flip that reaction. Let's see. Zinc yields zinc 2 plus 2 electrons. Okay? And now its voltage is 0.76. So it prefers this direction because that's positive. So if we add these two reactions together, we get this cathode and this anode together, and they produce 110 plus 1.1 volts is what we would expect under standard conditions for these two half cells connected in a galvanic cell. Okay, so that's a practical application of the standard reduction potentials. Now your book is going to tell you this. Once you decide which one's the cathode, which one's the anode, you take the cathode as is, standard potential, and subtract the anode. So that's what we did. We took this one minus a minus 0.76 gives us 1.1 volts. Now that's true. But I find it easier and more intuitive to write the half reactions together like this and say, all right, you can't add them this way. One of them's got to be flipped, right? Two reductions can't be added together. So if we flip this one, that one becomes a negative, and a negative gives you a negative value. That won't work. That's not spontaneous. So the other option is to flip this one, make that one positive. Now we get a positive value. That's the way it goes spontaneously. And then once you flip it, that automatically tells you which one's the anode, which one's the cathode. The standard potential, here's an important rule. The standard potential for a cell remains the same, even if you multiply these by some integer to get them to add together. For now, take it on faith. And the key here is that it's standard potential. The actual potential we'll deal with in just a few minutes, because concentrations are rarely 1 molar or 1 atmosphere gas pressure. And sometimes they're not even 25 degrees Celsius. So we need a way to take standard values and determine and calculate actual voltages. All right. The standard potential always remains the same, no matter what else you do. If you have that reduction, this oxidation and that reduction, put them together, the standard voltage is always this one. Okay? Now, that's not right. That's a unit of measure. The standard potential. There we go. That's correct. Okay, so for this one, if we write it this way, iron is being reduced. It's the cathode. So if we write iron as reduction here, it's 0.77 volts, standard potential. And then if we write copper this way, its standard potential is 0.34. Add them together and you get a positive value. That one is written correctly. Oh, excuse me. I'm sorry. These are reductions. So if we write copper this way, can we determine if that reaction is spontaneous? Yes. Take this one and flip it. Because it's written this way, copper is oxidized. So if copper is oxidized, that value is minus 0.34. Add those two values together, and you get 0.43. Yeah, 0.43. So this is written in a spontaneous direction. So if we're going to add them back together, in order to make these two half reactions fit the final reaction, we have to multiply this one by 2 because 2 electrons were transferred here. We need 2 electrons transferred here. But the state of potential is the same. Then when we add them together, we get this, and it's important to know how many electrons were transferred in order to calculate the actual potential. We need to know how many electrons were transferred. In this case, 2 moles of electrons were transferred in this balanced equation here. Okay? So you need to be able to calculate that, figure out how many electrons are transferred, and hang on to that number. All right. Right, that's just what I said. Calculation of the actual cell voltage using the Nernst equation. That's a man's name, Nernst. And we'll look at it in just a second. You also need to know the number of electrons transferred for stoichiometry purposes. In case we want to do, we want to reverse the reaction. Remember, we've studied that already. You can reverse reactions. In this case, you need to provide electrons with a voltage that's higher than the potential, the spontaneous potential. Then you can drive the reaction backwards. And in order to do any calculations, you need to know how many electrons are transferred in the process. That's called electrolysis. We'll talk about that also. Okay. So let's see what we've learned so far. Let's see if we can put these in order of strongest to weakest. Oxidizing agent. What does that mean? If we're going from strongest to weakest, oxidizing agent. What does that mean? Strongest to weakest. What would be the strongest oxidizing agent? The one that has the highest reduction potential. In other words, the one that wants to be reduced the most will make the best oxidizing agent. Okay, so we need to look at reduction potentials, and the greatest one, the strongest oxidizing agent, is the most easily reduced. So we order by the largest positive standard reduction potential, if at all possible. All right, so let's look at those. Let's see. We don't know values for sodium, fluorine, and iron because reduction potentials are not given in those terms. Here's how they are given. In other words, if we write the reductions and we're looking for the largest positive value, we would say, what do we know? Well, we know that F2 and 2 electrons is this value. And we know that sodium in electron is this value. And we know that chlorine and electrons are this value. And iron 3 plus with 3 electrons is that value. We get that from our charts. All right? So, that's not right. Oh, maybe it is right. We just don't know this one. Because we have to compare these species. We have to compare iron, sodium, F minus, sodium plus, and chlorine. Those are the ones we want to compare. We've got values for this one, and that one. Well, we don't yet, right? Reduction potentials start with the positive ion if necessary. So we've got this one gives us F minus right here, but it's the wrong direction. Let's see. These are the things we know, right? There's F minus. This came off the chart. There's sodium, right? There's sodium plus. There's chlorine. And there's iron, okay? So all of the species are represented by these values. Can we find the ones that we don't know, right? We want to know what's the reduction potential for this one. So in order to write the reduction potential, we need F minus reduced to 2 minus. We don't know. Don't know that. This one, let's see, we know that value, right? Still there. Now we need sodium reduced to Na minus. How about chlorine? Right, that's one of them. We keep that. Okay. How about iron? Well, iron, we need the other direction, don't we? Iron. We need to reduce iron. The problem with that is you don't reduce metals easily, right? They want to give up electrons. So their values are going to be extremely negative, if at all. All right. So if we look at the most negative value in here, it'd be a toss-up. The weakest would be, I would say, either this one or this one. So we're saying that based upon the position of sodium in this list, that sodium would be the weakest oxidizing agent, and iron would be the next weakest. Sodium plus, we can put that one there, it's a negative. And then chlorine is the next possible value. And then that one's possible. Why are we saying that is? This would be, taking that one, it would be extremely negative. Very, very negative. Because it starts out here and we flipped it to get there. So that's the weakest one. Okay. Cl2 is the strongest, stronger oxidizing agent than sodium, but the other species don't have standard reduction potentials to compare. So we sort of have to take an educated guess. right? So we can say the strongest is chlorine. Okay, so putting them in order is probably a tall order. I mean, that's very difficult to do with the information we have. Now, I suspect that there are sources, reference sources, that will actually give you these values. I mean, they're purely academic, as far as I know. But we can say that chlorine is the strongest oxidizing agent in there. And that comes in, that's practical. Straight chlorine gas is used as a powerful oxidizing agent, particularly in the manufacture of paper. They use chlorine gas, not just bleach. Bleach is a strong oxidizer too, but chlorine is even stronger. So they use straight chlorine in bleaching paper. Okay. So once we've got these galvanic cells constructed, and we know the balanced equation, there's a way to write the structure of the galvanic cell in an abbreviated form. That gives you a lot of information in a small space, and that's called line notation. Okay, we put the anode components on the left. That's where oxidation has occurred. The electrons originate from the anode and they cross the wire and they go to the cathode. So the line notation follows that convention. Anode on the left, cathode on the right. Okay? We separate the two by a double vertical line. And that indicates either a salt bridge or a porous disk. Now, what if the reaction is the cell, the battery, doesn't need a salt bridge, doesn't need a porous disk? Then you don't write the double line in there because it doesn't exist. Right? For instance, the lead acid battery under the hood of your car, it doesn't need a salt bridge because the anode and the cathode share the same solution, sulfuric acid. They're both immersed in that same solution. So there's no bridge required. The reactions take place at the surface of the electrodes. Right? That's a case where you don't have a double line. But when there's a salt bridge or a porous disk, a double line is placed in the middle to separate the two half cells. A single vertical line indicates difference in phase. Okay, so if you have a zinc metal submerged in zinc nitrate solution, then there will be a line between the zinc nitrate and the zinc to show separation of phase. And sometimes it's valuable to write somewhere above or below the line notation, the concentration of solutions that are being used. So for instance, in the anode, we are oxidizing magnesium metal to magnesium ions in solution. So we have a vertical line for a phase change. Then we need a salt bridge. And then on the cathode side, we're reducing aluminum 3+ ions in solution to aluminum metal. So there's a phase change there. Okay? This would be the anode side. This would be the cathode side. If we have an electrode in there that's not participating in the reaction, how do we write that in there? I guess we're going to show you later. I mentioned that earlier also. we need a chemically inert conductor. And it depends on the reaction. Very often a carbon rod will do. But if carbon is in one of the half reactions, you may or may not want to use it. Right? If it needs to be there, then yeah, it's there, it participates. But if it doesn't participate, it just serves as a conductor. Okay. How about this galvanic cell? If we're going to form a galvanic cell from these two half reactions, what do we need to do? We need to decide which one's the anode, which one's the cathode. Right? So, the way I do it is, if I flip this one, that makes this one negative, and the sum is negative. So you don't flip that one. This one is the reduction, which is the cathode. This one needs to be flipped, it's the anode. Now that's negative 0.77, and that gives us a positive value. So now this one is the anode. We flip that one and make it negative. There we go. And it produces a very, very low electrical potential. Right? Standard potential is only 0.03 volts. But that's for 1 molar concentration silver and 1 molar concentration iron 2 plus in its half set. Okay. Let's see. That's obvious from the discussion we've already had. Okay, so in this case, the half reaction for the anode occurs in solution entirely. All we need is a way to get the electrons from that reaction over to the other side. Right? So we use a platinum electrode here that doesn't participate in the reaction. We send the electrons over to the cathode, and silver in solution is reduced to silver metal, and it's plated out on the electrode. Now, what's obvious to me is the participant here is silver ion is being reduced to silver metal. So if this electrode were also platinum, then it would still work because the silver metal would be reduced to silver and played out on the platinum electrode. Okay? It's only when the electrode for the anode must be part of the reaction, consumed in the reaction, that the reaction won't go if you use a different electrode. In this case, the cathode, it doesn't matter. We can use silver or we can use platinum. Doesn't matter. Okay. Now, one thing that we're not showing here is the appropriate counter ions. Right? These are cations, so we need anions in there. Right? So if we start off with 1 molar 2 plus, then we need some anion in there. Right? We can't have electrostatic buildup. In other words, there has to be a balance of electrons, ions, ion charges. So we would have to have some counter ion in there. We would also have to have some counter ion in here. And the most efficient way is to use a counter ion that's common to both. And there's also the consideration of solubility, right? If you're going to have silver ions in solution, you're limited. You can't use chloride. Silver chloride is a solid, so it won't be in solution. Silver nitrate would be a good choice. All nitrates are soluble. So silver nitrate and iron 2 nitrate would be a good choice as the counter ions. Okay, line notation here. platinum, let's see. Here's the bridge between these two half cells. Platinum does not participate in this reaction, but these components are in the same phase. Even though they're part of the anode, they're in the same phase. So we can't put a line between them. So we use a comma to separate them. And then this is a phase change between solid and aqueous. And that platinum does not participate in the half cell. It's separated out here by itself. So, by my way of thinking, when we write it this way, solid, then we have iron 3+ to iron 2+. These are aqueous. Like that. And then we have silver in solution. And then a phase change to silver electrode. Okay, the way I look at it, the way electrons flow, the electrons flow, they don't flow from here to here. This is a salt bridge. The electrons flow externally. So I imagine a wire connected here. That's how I keep things straight in this line notation. So the electrons would flow from the platinum electrode over to the silver electrode. That's why the platinum is on the left-hand side, over here. And this reaction, since it's the anode, it doesn't matter which way you put these. Because if it's the anode, then you know which way they're going, right? In this case, the electrons are moving from here. Or this one is being oxidized from here to here, releasing electrons that go through the platinum electrode over here to the silver. And then electrons are flowing into this reaction to reduce silver. So that's how I keep this notation straight in my own head. Okay. Let's see how we're doing on time. All right, we're still pretty good. Got a couple more topics. Okay. So when we're putting together our galvanic cell, our battery, these are just reminders. If you got two reduction potentials and you're going to try to construct a galvanic cell from these two reactions, you flip the one that makes an anode because the summation of the two potentials gives you a positive value. So if you flip one and it gives you a negative summation, you flip the wrong one. Go back and flip the other one. That makes it the anode, and the one you didn't flip, the cathode. Now you've got them in the proper order, and you know their standard potential. Then you can write the balanced equation as a composite of those two half cells. By the way, we've done it before, right? In balancing the redox equations. In fact, the half reaction may require some addition of water and hydrogen ions, or maybe hydroxyls, whatever it takes to get those two equations together and balanced. And then don't forget, make a note of how many electrons are transferred in that reaction. Okay. So in this case, this drawing includes the potential of the cell, the direction of the electron flow, and labels. So this is how you would draw a picture of what's going on. And you got a voltmeter up here measuring everything. Electrons are moving from the anode to the cathode. And if this is standard conditions, we're saying, okay, this is 1 molar silver. This is 1 molar copper 2 plus. This is a copper electrode that participates in the reaction. This is a silver electrode that participates in the reaction, but we already know that on the cathode side, it doesn't have to be silver. Only if you want to run it backwards does it need to be silver. If you're letting it go spontaneously, this could be platinum. Doesn't matter. Now, what's the voltage? Well, we write this one as an oxidation, right? So there we flip the voltage. And this one is the cathode. Let's see. Hold on a second. I don't use this very often, so I have to go remind myself. Yeah, cathode minus the anode. Okay, and minus the voltage for this side gives us a standard potential of 0.46 volts for this cell. Right, 25 degrees Celsius, 1 molar concentration, and there are no gases, so we don't have to worry about that. Now the salt bridge is there just to maintain balance. And it seems to work best if you use some counter ion that's common to both. Sodium is okay, and nitrate is okay. Nitrate is probably the best, because if you use chloride in here, then chloride is going to leak out here and precipitate your silver and ruin your cell. So that has to be considered also. Okay. So let's look at this from the perspective of Le Chatelier. Right? We have a situation where we want to say, all right, what would happen if we change the concentrations of each side? Okay. If we increase the copper concentration, okay, we're over here on this side. If we increase the copper concentration on this side, what does that do to the half reaction of copper? Well, here's our half reaction for the anode. Copper is being oxidized to copper 2 plus. If we add more copper in solution, it's going to drive the reaction back to copper and consume electrons in the process. So that should decrease the voltage. We're not sending as many electrons across, and the push is less. So the voltage should decrease. Okay? Okay, now let's sit on that for just a second and look at some thermodynamic considerations. First statement, just out of the blue, the cell potential and the work, the signs of those two values are opposites. Remember when we said potential? A spontaneous reaction is a cell potential that has a positive value. Okay. With work being negative, why would we make work negative? Because if the reaction is spontaneous, think of the reaction as our system. We want to extract work from the system, right? If we're extracting work, it has to be a negative sign. But in order to get that work done, the potential has to be positive. Okay? So that's a way to rationalize the variation in the symbols. The electrical potential is positive for spontaneous reaction, and when it's spontaneous, now we can get work out of it. So work is leaving the system and has a negative value. Okay? So, remember what we said earlier. 1 volt equals 1 joule per coulomb. Okay? This is another way of showing that. The electrical potential is equal to the work, which has to be negative, and the charge, which is Q. Now, I know earlier in Chem 101, we used Q as designating heat. But in this scenario, Q now is charge. Q is the value of coulombs, charge. W is the value of work. All right? So, if we solve this equation for work, then potential times charge is equal to, or QE is equal to the value of work that we can extract from that process. And in fact, once we know the maximum amount of voltage that can be obtained, and that's best measured if you have to measure it with a potentiometer. That gives you the maximum electrical potential from that reaction. That will also give us the maximum work available for that reaction. Well, we're going to move the sign like that. So the maximum amount of work is equal to the negative potential times the amount of charge transferred. Right, and I already showed you that one. The reason for this is because everything is referenced to the system. Okay, units of measure. I showed you this one earlier also. Voltage, joules, coulombs. And then we can interchange these if we use those units. All right. So let's see. Just to remind you, the cell potential and work have opposite signs. For a spontaneous process, the potential will be positive, the work will be negative. So that's why this negative sign is out here, to make this positive spontaneous voltage into a negative value. Or if this were negative, then you would have positive maximum work, which means you'd have to do work on the system. That would be a non-spontaneous reaction. Okay, the next point is, this is the maximum work that can be obtained. That never happens. There is always some loss, some waste somewhere. And it can happen for various reasons. It could be simply thermodynamic. Right? We studied that in Chem 101 with entropy. You never get maximum work since there's entropy. Remember? The Gibbs free energy, the maximum amount of energy that's obtained from a reaction, is the enthalpy minus T times the entropy. So you subtract the entropy from that, and that's where you get, this is the maximum work, which would be equal to that maximum work. Okay, so I sort of contradicted myself there. We've already taken into account entropy when we get to this point. So there are other factors that would reduce the useful work. For batteries, there's a concept called internal resistance. There is a resistance built into every battery that opposes the movement of electrons in it, right? Based upon its intrinsic composition. So you never get the maximum amount of work out of a battery for that reason. And that internal resistance changes with temperature in particular. Right? If you increase the temperature of your battery, Now, let's see. I better not go there right now. That's a little too complicated for us at this stage. All right, let's go back to this topic. We can calculate the work obtained from a process if we know the voltage, the electromotive force, and the amount of charge transferred. Now this E doesn't have to be standard. It can be E at any concentration. We just need to know what it is, or we need to be able to calculate what it is. The actual potential difference at the time current is flowing. And Q is the quantity of charge in coulombs transferred. Okay? Now, if we're going to do any stoichiometry, we need to know the relationship between coulombs and moles of electrons, because electrons are carrying the charge from one reaction to the other, one half cell to the other half cell. So this is the equivalence. Is called the Faraday. Is the charge on 1 mole of electrons. So 1 mole of electrons is calibrated to deliver 96,485 coulombs of charge, right? So it takes a lot of electrons to make 1 coulomb, right? Because a mole of electrons is how many? 6 times 10 to the 23rd electrons. And this is 10 to the 5th. Actually, it's almost 10 to the 6th. So 10 to the 6th, 10 to the 23rd would be 17. 17 orders of magnitude, right? 10 to the 17th electrons to produce 1 coulomb. But this is the relationship here. And that value should be in your useful information. Let me check just to be sure. In the back of your review document and on the back pages of every exam will be exactly the same. So let's see, units. There it is. 1 Faraday equals 96,485 coulombs per mole of electrons. Okay? We need that for stoichiometry because this relates to the voltage and this relates to the moles of product or reactant consumed, product produced. We've got to know that relationship. Okay. All right, this is true. This maximum work that can be done is related to the Gibbs free energy. Right? So there you have W max is equal to the Gibbs free energy. So we can set these two values equal to one another. Right? This minus Q, E max equals delta G. So do the signs match? For a spontaneous reaction, voltage has to be positive, okay? For a spontaneous reaction, remember, delta G has to be negative. So a negative QE equals that's spontaneous. So the units, the signs of the units are properly represented there. Okay, we also know that 1 Faraday, right? 1 Faraday is related to moles of electrons. As, let's see. Well, the charge divided by the moles. So there's a relationship, only we haven't put numbers in it yet. So if we say Q, let's see, minus Q equals E max. And we're going to substitute moles Faraday in for the Q. So now we have delta G equals negative N of moles of charge transferred, of moles of electrons actually, and the Faraday unit, which is 90, let's see, 90, what is that value? I forgot already. Let's just look it up, 96,485. 96,485 coulombs per mole. Okay, that's what 1 Faraday equals. Okay, so not to muddy the waters, but we have an equivalence here. The Gibbs free energy is equal to negative moles of electrons times the Faraday unit, this right here, times the maximum voltage. So that being the case, that would be true. That would give us Q, or the charge in coulombs, right? Because moles of electrons cancel moles in the Faraday unit, and that's true. Okay. So there's Michael Faraday in his younger days. This man was a genius at experimentation. He could take a concept and devise a laboratory experiment that would answer a question the best of anybody, of any of his peers. So if you hear his name praised for any reason, it's probably true. Okay. Let's see. Okay, it's all on the screen, so I don't have to keep it up here. All right, so here's our relationship. Delta G0 equals negative moles of electrons times the Faraday times standard electrode potential. In this case, if delta G is negative, then the process is spontaneous. Right? And if E is positive, then it's also spontaneous. But this will also hold for non-standard conditions. And if we change the conditions of the cells, the concentrations of the cells, that will give us a different E value, then we may end up with a cell is not spontaneous. Vice versa. We may have a cell that at standard conditions is not spontaneous. But if we change the conditions, we may make a non-spontaneous cell run spontaneously. That's possible. Now, we were going to do this one in the lab. One of the ways that we can demonstrate that is what's called a concentration cell. Both half cells are exactly the same with their basic chemistry. The only difference between them is the concentration. So their standard potentials of this cell and that cell are equal. That means the standard voltage is 0. So how do we get that cell to run spontaneously? Well, we balance the concentrations so that the actual voltage is positive. And in this case, in order to make it run in a positive from anode to cathode, the anode needs to be a lower concentration than the cathode. Okay? Why? Because if this is lower concentration, then we're putting silver ions into solution to increase this one. and we're dragging silver ions out of this one to plate on the electrode. It's a equilibrium problem. Okay, let's see. That's true. Le Chatelier's rule says that we're going to increase the silver on this side and decrease it on that side until they're equal in concentration. When that happens, the cell's dead. The reaction stops. Okay. So how do we calculate the actual voltage? Well, we owe that line of work to Walter Hermann Nernst. He was a German chemist. He worked in a lot of different things: thermodynamics, physical chemistry, electrochemistry, solid state physics. He had his hands in lots of pies. He was instrumental in working with and helping to formulate the third law of thermodynamics. We're not going to worry about that right now. But he won a Nobel Prize in 1920 for that work in thermodynamics. His Nernst equation is extremely useful for calculating the actual voltage of a galvanic cell. All right. So the relationship here that Nernst derived is based upon the standard potential and then modified with this part of the equation, which takes into account both the temperature, the number of moles of electrons transferred. Aha, remember that? The number of moles transferred, the Faraday constant, and Q. So we need to have the balanced equation and the actual concentrations of our components so that we can calculate Q, right? If it's at equilibrium, we can calculate K. But if it's at equilibrium, then there's no potential, right? We're stuck. At equilibrium, there's no movement in either direction that can be detected in our external circuit. So we have to calculate Q, and that will tell us also which way the reaction is moving. Okay, so the value of R has to be the one with joules in it, 8.3145 mole K. And then there's the Faraday. Temperature has to be in K units, and N is the moles of electrons that are transferred. Okay, this allows us to relate the electrical potential, which is a physical concept, with which actually electrical potential doesn't have to have chemistry. But if we're going to relate it to chemistry, we have to know the stoichiometry of the reaction. And for that, our connection is how many moles are transferred. Well, in addition to the Q. Okay, so there are two ways that we're connected: moles of electrons transferred and the Q of the reaction. Okay. The problem here for general chemistry students and professors alike is that I don't want to have to calculate this thing every time. Faraday is a constant, R is a constant. Temperature could change, but let's simplify it. Let's say always standard temperature, 25 degrees. If we do that, then we can input this constant R, temperature of 25 degrees, and the Faraday constant, and now we come up with this single value, 0.0591, divided by the number of moles of electrons transferred, and then the Q. So now all we need to know is the standard potential, the moles transferred in the balanced equation, and the Q at the beginning. What is the Q for the reaction? Then we can calculate E. And that makes it a lot easier. So we always assume with this type of arrangement, this equation, that the temperature is 25 degrees Celsius. Okay. Oh, I left out one step. We also convert the natural log to the common log. Common log is easier to work with sometimes. So the common log of Q here, rather than the natural log of Q. And this is just a proof for that conversion factor right here. Right. We're not going to go through that. I just thought you might be interested in case you want to run through it and say, okay, yeah, I believe it. Or you can just take me at my word. Okay. So at 25 degrees and equilibrium, Q equals K and E is 0. And the equation bears that out. Right? It doesn't matter what N is. The voltage is going to be 0. So the standard potential is going to be equal to these terms with the K value. So this is interesting. If you've identified your equation, balanced it, and you've calculated the standard potential or measured a potential, whatever the case may be, then you can calculate the K value. What is the equilibrium constant for that reaction? Or if you've calculated the K for that reaction by some other means, you can determine what should be the standard potential. So they're related that way also. All right. So let's take this example. Say we have this ion. Let's see. No, this one is thiosulfate. I'm not sure what that one is. This reaction. So we're taking, let's see. Oh, here's our half reactions. Okay. So these are the two half reactions. Which one's the anode and which one's the cathode? Well, if we turn this one, if we flip this one, then that makes them both negative and that won't work. So we got to flip this one and make it the anode. And that makes sense. If we write it this way, then chromium 2 plus becomes chromium 3 plus. It is oxidized. So this one becomes positive, and now the standard voltage is a positive 0.67. Okay? Now, how many electrons were transferred? Right? If we write this one as a reduction, in order to transfer the right number of electrons, all we have to do is multiply this one by 2. Now we know that 2 moles of electrons are transferred for the balanced equation. Okay? And the standard potential is 0.67 volts. Okay, let's see. N equals 2. All right. So if we want to solve this equation for K, let's see. Right, we had this one before. We had E0 equals 0.0591 divided by N, and times the common log of K. So now if we solve it for this one, that means this comes over here. And this is 0.0591. That's log K. Right? So now we substitute 2 moles for this, 0.67 for the standard potential, and we calculate the log of K is 22.6. So K would be the anti-log of 22.6. 4 times 10 to the 22nd is the K value for this reaction. Very large equilibrium constant driving this reaction. So we know that the way it is written, that it favors products. The K value says favors products at equilibrium. So that confirms that E0 is a positive value, which means it's spontaneous. We could calculate the delta G and find that it's a negative value. Okay. So all of those factors confirm that this is a spontaneous reaction. When the cell is at equilibrium, E is 0. E0 is equal for concentration cells because they're exactly the same standard potential for both cells. Concentration doesn't matter because E0 is always 1 molar, 1 molar. Okay. So let's take this example. Let's say a concentration cell is constructed from a half cell on both sides. All right. We're going to have nickel 2+ in solution and a nickel electrode. And one of the cells is going to be 1 molar. And the other cell is going to be 10 to the -4th molar. So which one's which? Which is the cathode and which is the anode? The cathode is always the higher concentration. The anode is 10 to the -4th. Okay. So we know that we've got these little subscripts in here to help keep them separated when we combine them. So this is the cathode where reduction takes place. This is the anode where oxidation takes place. This is the low concentration. This is the high concentration. So if we combine those two, we know that 2 electrons are being transferred in this balanced equation, right? That's our N value. So if we calculate the actual potential based upon E0, E0 is 0, right? Standard potential for concentration cell is 0. So this term drops out. Now we have these here transferred over here. Now we know that Q is this value divided by this value. Why? Because in equilibrium calculations, solids and pure liquids are left out. Right? So that's why we only have these 2 terms. What's the concentration of nickel ions in the anode? It's 0. It's a 10 to the -4th. Cathode is 1. So we have 10 to the -4th divided by 1. Here's this term right there. Then we have our constant here. We have our 2 substituted for N. And then we just solve it for E. And it turns out that the voltage for that cell should be 0.118 volts. Okay. Let's see. Okay, we're doing a concept check. A nickel electrode in 1 molar, nickel 2+, standard potential. Standard potential for this one is 0.23, standard reduction potential. Silver electrode has a standard reduction potential of 0.8. Okay. So sketch this cell. What would the cell look like? Right. Which one's the anode and which one's the cathode? Well, let's see. If this one is flipped, makes it positive, that would give us a positive value. If this one's flipped, you get a negative. So we're going to flip this one. So we need the anode is actually nickel in solution. Okay, and our nickel electrode, there we go. And that goes over to our cathode. And this one is silver. Okay, and in this solution, we have silver ions in aqueous solution. And then we have a salt bridge. There we go. I forgot the meter here. Okay, so that would be, and the electrons will flow this direction. Reduction takes place at the cathode, oxidation at the anode. And the concentration here is 1 molar. 1 molar. At the start, okay, the concentrations will change over time. Over here, the concentration will increase because we are oxidizing nickel metal into nickel ions. Over here, the concentration of silver ions will decrease as we oxidize, as we reduce silver ions to silver metal. Okay. Oh, I was supposed to draw the, well, it's too late. Draw the line notation. So here we have nickel on the left, silver solid on the right. Electrons are flowing from here. They're going here, here. Electrons flowing here, here, here. Okay. Oh, I did draw it. Okay, so this is what it would look like if you draw it out longhand. Actually, I did this on a computer. And we use silver nitrate here and nickel nitrate here. So the counter ions are nitrates. What about the salt bridge? Sodium nitrate is a good choice, especially since we've got silver there. Okay, and the voltage is this one, change the sign. So our voltage is 1.03 volts. So I ought to get about 1 volt out of this cell under standard conditions. All right, so let's look at some other uses. I mentioned earlier the lead acid battery, or sometimes they call it the lead storage battery. Notice that we have lead oxide cathode, and the anode is made out of pure lead. So the anode is made out of pure lead. Let's just write that up here. Anode is made out of pure lead. It's going to be oxidized. It's going to lose electrons. Right. So many electrons here, but it produces what? 2+, I believe, in aqueous solution. Okay, cathode is going to take lead oxide. So what is the oxidation state on that lead? Oxygen is 2-. There are 2 of them, so there's -4. So that lead has to be this one. I'm not sure about this, whether it's aqueous or not. I don't think it is. We're going to add electrodes to that and make lead 2+. Okay. So notice we ended up in the same place on both sides. Well, as it turns out, the electrolyte, the solution in which both of these plates are immersed is sulfuric acid, H2SO4. So we've got these sulfate ions floating around. Well, as it turns out, sulfate and lead form a solid. So the sulfates combine with this one or with this one and produce lead 2 sulfate on one plate, lead 2 sulfate on the other plate. Okay? And we don't need a salt bridge because they're immersed in the same electrolyte. Well, I guess that's all they want to say about that. Here's a dry cell battery. You can buy these at any retailer. In this particular reaction, let's see, the anode is zinc, which means zinc is going to be oxidized. And the cathode is this paste of manganese, 4 oxide and ammonium chloride. And the carbon in the middle is the site, the cathode. That's the site of reduction. It takes place right at the surface here. All right, we're not going to give you any more details about that, I guess. There's another type of battery. This one has mercury in it, so you won't see this one on the grocer's shelf. The EPA frowns on this thing. But there are substitutes, other reactions that can be used in these types of batteries, little button batteries. The really tiny ones are the ones you'll see people putting in their hearing aids. Okay, here's another type of galvanic cell, I guess you would say. It's called a fuel cell. The advantage to fuel cells is that as long as you keep providing hydrogen this side and oxygen this side, you'll never run out of electricity. In other words, you don't have static solutions that can be depleted. You just keep pumping this in one side and that in the other side, and the reaction produces water. So the fuel cell combines hydrogen gas, oxygen gas, makes water, and transfers electrons that can drive machines. The problem with these are more engineering than they are chemistry, because these things have to operate at extremely high temperatures. So they're dangerous with for that reason only. But it's difficult to maintain those high temperatures in motor vehicles. They use the fuel cells in spacecraft. In the Mercury, Gemini, and Apollo series spacecraft, fuel cells were used to power them. They didn't use photovoltaic cells. They used fuel cells. So various things have to be, the chemistry has to be modified perhaps to reduce the temperature, but also if you're going to use hydrogen as your fuel source, if you're going to put it in a car, you need not only a way to store large amounts of it, but to store it safely, because cars are eventually going to get into a collision, a wreck. And if you don't have safety precautions for your hydrogen, then you could have a big explosion. So there are various technologies that are being investigated for that also. All right, so let's look at naturally occurring galvanic cells. And we give those the name corrosion. So corrosion is the process of a redox reaction that changes a metal into a less desirable form, usually an oxide. For instance, iron. Right? Iron is essential to modern civilization. We build everything out of it, from our buildings to our automobiles. If not protected in some form or fashion, this iron can combine with oxygen and produce rust. Okay, that equation is not balanced. Let's see, maybe I can. If we need 3 of these, that means 3 halves here, 2 here, and then we just need to get rid of that half and balance it. But that can happen to any metal. Iron is central to our civilization, so we need to know something about it. On the surface of iron, where it's exposed to an oxidizing environment, oxygen in particular, as long as there's moisture there, we set up an environment for a galvanic cell. And wherever that water droplet lands, oxygen combines with the iron to make rust. This is, let's see. This is the anode reaction, right? Actually, that says that this is different. That says that Fe2O3. There. So that's what they're saying. In which case we need half of this one. But there are reactions beyond that. This reaction will also proceed to iron 3+. So this is the first step. And in the anodic section, we are oxidizing iron to iron 2+. So it's being consumed. And over here in the cathode, we're taking oxygen and reducing oxygen to a 2-. So we're going from 0 to 2-. And the combination of the two produces FeO, iron oxide. Okay, how do we prevent corrosion? How do we stop that from happening? Well, one way is to protect the metal, in this case iron, protect the metal from the oxidizing environment, right? Just seal it off, paint it. The other way we can do it, one way is we can galvanize it. In other words, coat it in zinc. Zinc is a more active metal. In other words, it wants to be oxidized more readily than iron does. So the zinc sacrifices itself to become zinc oxide instead of the iron underneath. We can form an alloy of metals. Let's stick to iron. Iron plus chromium. Originally, it was 35% chromium by mass, was stainless steel. Chromium is more active. It wants to be oxidized more readily than iron does. So you can see that from the standard reduction potentials. And what happens is, if the surface is exposed to air, the reaction of chromium with oxygen is almost instantaneous. It seals the surface so that oxygen now can't get to the iron. If you scratch the surface, the reaction, the healing reaction, is almost instantaneous. It seals it. So that alloying process also works. Another process called cathodic protection. And that's similar to what we've discussed so far, except that the sacrificial metal that's being oxidized is connected to the iron, say, through a wire. And as the anode, the metal, is being consumed, it's producing free electrons that transfer through the wire to the iron, say, pipe, and keep it reduced. And that's the way that buried tanks and pipelines were once protected. And many still are. Most buried tanks now they're replacing them with polymer-based, like fiberglass and polyethylene, polypropylene concoctions, so that they don't suffer from this corrosion problem. But some things you can't. I mean, some pipelines are made out of metal and they're going to stay metal. They're going to stay iron. Ship hulls are made out of steel, basically iron. And salt water is very corrosive. It promotes that galvanic corrosion problem. So what you'll see is around the body of a ship is a band of zinc. And zinc sacrifices itself. It becomes corroded and delivers electrons into the hull and maintains the integrity of the iron in the hull. Now, when the ship is underway, when it has power, a trickle of electrons is delivered to this zinc strip and transmitted from the zinc into the iron and maintains both the zinc and the iron in a reduced state. The only time the zinc is consumed is when the ship is docked and power is turned off, which is rare, but it's there just in case. Okay, this is the cathodic protection. The cathode is actually the pipe. The anode is, in this case, magnesium. Zinc would probably work also. Okay, now to the topic of electrolysis. I think that's the last one in our discussion. Yes, electrolysis. This is chemistry electrolysis. This is not cosmetology electrolysis. You remove unwanted facial hair. In this case, electrolysis can be viewed as the reverse reaction to the galvanic cell. So that automatically means that the reaction that's being used for electrolysis is the opposite of the galvanic cell balanced equation. You run it in reverse, so it's not spontaneous, right? We know that the galvanic cell if written from left to right, is going to have a positive E value. It's spontaneous that way. Certain voltage. The electrolytic cell would be the reverse. Right? So the voltage here has to be greater than the voltage here. Okay? If it's just equal to it, then the reaction is stationary. No reaction occurs at all, either direction. So you have to exceed the voltage by a little bit in order to make it go backwards. So we run the reaction in reverse, and it's not spontaneous. But that doesn't mean it can't be useful, right? Suppose we want to force the deposition of a metal from a solution, but the reaction is spontaneous in the wrong direction. we apply a voltage in the direction we want, and we can deposit metal cathodically. Right? We're going to reduce the ion from solution to the metal, and it deposits on the cathode. Okay, perfect example, except that they don't do it much anymore, except on classic automobiles. Bumpers for automobiles have been present almost from the beginning of the invention of the automobile. But eventually, a style entered in, and you don't much want your car to be have bumpers on the front and the back that are all rusting out steel chunks. You can make them thick enough so that they can rust all they want, and you still have protection. But rather than do that, we coat those steel bumpers originally with chromium. So we take chromium ions from solution, we make the bumper the cathode, we drive electrons into the cathode that reduce the chromium at the bumper, and they plate out on that bumper. And then we slap them on our car, and it looks nice, bright, shiny, new. Now we've got all plastic bumpers with pistons and superstructure underneath, and it's not the same. Okay, so the question becomes, for electrolysis in particular, what voltage, how much charge has to be transferred to deposit a certain amount of metal on a surface, on an electrode? So this is the calculation that you might want, that you will have to do to solve some problems. We need to know if the voltage is high enough, and it doesn't matter how high the voltage is, you just want it high enough to drive the reaction in reverse. Once that's established, then what you need to know is the current. Right? How many coulombs per second? Coulombs per second is the ampere. So 1 coulomb per second is 1 ampere. That's current. How fast is the current moving? Per second passes this point, so many coulombs per second. Once we know that, then we can determine and how long it takes, how much time evolved with that current. Then that gives us the quantity of charge. Then we use the Faraday to determine how many moles of electrons are required to move in this reaction. Moles of electrons. Then we use the stoichiometry of our balanced equation. Well, in this case, copper, but any metal. The moles of electrons related to the reducing or the cathode reaction to produce the metal. How many moles of electrons will produce moles of the metal? What's the ratio? And then we convert moles to grams, and that will tell us the mass of the metal that is deposited. Okay. Right, so we need to know what an amp is, and we need to know what a Faraday is here. And then the measurements. All right, so here's an example. Let's say we have an unknown metal, M, is electrolyzed, that it is reduced from solution at the cathode to make the metal. Okay, here's our metal. We're going to make the metal here solid, and in order to do that, see. I don't recognize that symbol. Hazelwood. Wrong party. Okay, so here's the scenario. We've got this ion is being electrolyzed. And we want to find out what's the metal. Well, here's the clue. One metal atom requires 3 nitrates. So that means this is a +3 charge, right? +3 charge needs 3 1- charges. So that's the key. That tells us how many electrons are required to make that metal. Okay, now the time measured is 52.8 seconds. Time 52.8 seconds. The current is 2 amps. So current is, in physics, current is a big I. I equals 2.0 amps. That's a lot of current. Very high current. You don't want that much current going through your body unless you want to die. And then 0.0719 grams of metal from the solution we're depositing. So the mass of the metal is 0.0719 grams. Okay. How do we determine the metal? How do we know what that metal is? Right? From the periodic table, if we know the atomic number, the number of protons, easy. We just run down the list until we find that number. But almost as good is the molar mass of the material. Right? What does a mole of this metal weigh? And that's useful also. So we want to know the molar mass is the mass per moles. Okay, so we need to know the moles of this that are reduced in this amount of time. All right. So if we got this many seconds, this many amps, then I times T, this is coulombs per second, this is seconds, will give us the number of coulombs, right? So we need 52.8 seconds times 2 amps is equal to what? $52.8 and 2 times is 105.6. 105.6. Yep. 105.6 coulombs. Okay. Now we need to know that charge is equal to how many moles of electrons. Right? And a coulomb, a Faraday, is equal to 96,345 coulombs per mole of electrons. All right? So if this is coulombs, we need to change that into moles of electrons. So coulombs on the bottom, moles of electrons on the top. So 1 mole, 96,345 coulombs per mole. Okay. 96,345. I get 1.096 times 10 to the minus 3 moles of electrons. So what's the ratio? For every 3 moles of electrons, you get 1 mole of metal. So now we can find out the moles of metal. We know the mass right here. Now we need the moles. So the conversion factor here is moles of electron per mole of metal. Well, actually, it's the same. Moles of M. Okay, so the ratio is 3 electrons for every one of those. So we divide this number by 3, and we get 3.654 times 10 to the minus 4th moles of M. So now the molecular weight of the molar mass is equal to mass grams per mole. 3.654 times 10 to the minus 4th moles equals what? 0.0719. And I get 197 grams per mole. So we look on our periodic table and look for 197. The closest I come to that one is gold. Has a molar mass almost 197. Okay. Come on, there we go. So this is the calculation on the slides that I did up here. Might be easier to follow here. So this is the relationship of moles of electrons to moles of metal. And this is how you find the moles of electrons. Right? We're using, this is our amperage. This is how long it ran. Cancels the S's. And this one converts coulombs to moles of electrons. This converts moles of electrons to moles of metal. And then we put it in the calculation, and there you have it. Okay. So that was electrolysis. Oh, we're still on electrolysis. Consider a solution containing 0.1 molar of each of the following. Predict the order in which the metals played out as the voltage is turned up from 0. Okay. That's the first question you ask yourself. Where do the metals form? They form on the cathode, which means reduction. So we looked at the reduction potential, and we increased the voltage. The cathode is the site of the reaction. Okay, that's right. Reduction potentials will predict the order of plating. Right? So the more positive standard reduction potentials plate first as the voltage is increased. Why? Because positive means spontaneous. So the more positive value will plate first as we turn the voltage up. And they plate out in this order. Copper first, lead, tin, nickel, and zinc last. So that's one way you can separate metals from this solution. Right? Earlier, I think maybe in Chem 101, we talked about separating elements, metals in solution based upon their solubilities. Right? That's one way to do it. This is another way. If they're all metals, then you can separate them using electrolysis. All right. These are some commercial applications of electrolysis, right? Running spontaneous reactions in reverse. Production of aluminum is probably the biggest in the world. And it actually transformed the modern world. Production of aluminum, when it was first discovered, was produced by chemical means. And it was very expensive. In fact, the King of France impressed his guests by bringing out the aluminum flatware. No silver, no gold, aluminum. Aluminum cost more than gold in those days. It wasn't until Hall, I forget his first name. He started working on these things as in high school. No, I take that back. He was an undergraduate. Started working on the production of aluminum using electrolytic means. In other words, reducing aluminum from solution of some kind by passing an electrical current through it. And that brought the price of aluminum down so far that now we wrap our food in it and throw it away when we're finished. Aluminum foil. We can purify metals. We already saw that one in the previous slide. We can plate things with metal, right? Plate bumpers with chrome. We can plate cheap metal rings with expensive metals on the surface. Like we can plate a very, very thin microscopic layer of gold on, say, silver underneath. And it looks good for a while until your finger wears off the gold, and then you see the silver underneath. Industry also electrolyzes sodium chloride. How do you do that? How do you electrolyze a solid? You don't. You melt the solid. You heat sodium chloride up so hot that it melts. Then you pass a current through it. And it produces sodium metal and chlorine gas at the different electrodes. I think I've got a picture of that here. You also, when you produce chlorine gas, that's useful. You can make bleach out of it. You just take sodium, dissolve it in water, make sodium hydroxide, and then bubble chlorine through it, and you get bleach. So here's the Hall process. It was modified by this Frenchman a little later. The trick for making this useful was reducing the melting point of aluminum oxide. Purified bauxite is the ore. So sodium aluminum fluoride was added to the mixture to reduce the melting point, so you wouldn't have to heat it so high to get it to melt. And then you just run electricity through it, and the molten aluminum drops off the graphite electrodes, and these electrodes are consumed in the process. And then you just knock off the plug and you got molten aluminum come out the bottom. These are the particulars. Aluminum oxide melts at 2,000 degrees Celsius, pretty hot. If you add 89.5% cryolite, which is the name for this compound, sodium aluminum fluoride, and only 10% of aluminum oxide, then you can bring the melting point down to less than half of that. And that requires less energy to start the process. But it takes a lot of electricity to do this. So aluminum processing plants like Alcoa historically located their processing plants, their smelters, so to speak, near sources of cheap electricity. So hydroelectric, that was provided cheaply by the government, was a good place, like in the Tennessee Valley, they have plants there, or in areas where coal is abundant and cheap, and you can make electricity with that. So in southwestern Pennsylvania, Alcoa has some outfits there. We can electroplate this spoon with silver. Right? We just need a chunk of silver, run the power backwards, and plate the silver on that spoon. You can also reduce corrosion on bona fide silverware. You just take a baking dish, put aluminum foil on the bottom, put a layer of water in it, add salt, and then lay your silverware on that aluminum so they touch. And the electrolytic process will convert the silver compounds. Silver oxide, usually silver sulfide is more common. We'll convert that to silver metal and remove all the corrosion from your silverware. This is not stainless steel flatware we're talking about. This is silverware. Okay, oops, missed one. Okay, here we electrolyze molten sodium chloride. So the anode is where we oxidize chloride. Right? So at the anode, you get this in solution. Actually, it's not aqueous. It's in solution somehow. And then we, oxidize it, excuse me. We oxidize that and produce chlorine gas plus electrons. Okay? So this is at the anode. Let's see, we need two of those and two of these. And at the cathode, you produce sodium. So we have sodium ions, and we add electrons, produce sodium metal. Okay? And the reason we separate, this is molten sodium chloride, and calcium chloride is added for the same reason as cryolite was added to the aluminum oxide, to reduce the melting point. So we have these cathodes here, and the anode is here arranged in such a way that the gas can bubble out, can escape, and we can capture it. And over here, we produce liquid sodium. And I'm assuming from this drawing that sodium metal is less dense than sodium chloride, molten sodium chloride. So it floats out. Now, I don't know that to be the case, but based upon this scenario, that's my guess. Okay, that's it. All done with chapter 18, electrochemistry. And there are problems. I think the review document that I'm focusing on is this version 2? Yes, version 2. There's a version 1 and there's a version 2 in Blackboard. And version 2 is the one I focus on. That's the one I'm going to use when we come back for review. Okay, that's it. And that's all over, but exam 7. And let's see, are we going to have a final? Let me check to be sure. No, we're going to have exam 7. I've scheduled it for December 6th, but it depends on the school when they want us to have it. But if all else stays the same, then December 6th we'll meet for this exam, and there will be no final. This will be the final exam.